Well, hello and welcome back to Old School Coding, where I'm using techniques from the 1990s with a computer language from the 1990s and tools largely from the 1990s to construct a simulator for a microcomputer system from the 1990s. So, old school stuff. Today, I'm going to try to implement the move immediate instruction, which will move us into, you see what I did there, the next stage of the simulation where we need to have a immediate parameter, immediate argument that is provided in the second machine cycle. So this is our first instruction that has a second machine cycle. And we can see here on this diagram, which it occurred to me today, that this could have been microcoded. So I could have analyzed all of these and designed an appropriate, very long data word microcode. And that would be hardware engineering techniques from the late 80s, early 90s that would involve there. And our address decode would basically be given the instruction, we would then set up this VLIW thing, which would then have a bunch of signals out, each one of which would drive a behavior. But not doing that. Instead, I'm using the instruction to select a function. So how we're going to do this second cycle, why are pages 16 and 17 not aligned? I thought these were, I guess the scan isn't aligned. I've been looking at this so much, I just thought they were perfectly aligned. That apparently was wrong. Anyway, so move immediate data. We've got the opcode here. We will have a T4 cycle that does nothing in M1, but that T4 cycle needs to pick up a M2 cycle. And during M2, it's going to look like the beginning of M1 in some ways. We're going to have we're going to send out the PC. We're going to give a status word that's going to be, that says status word 6. We will refer back to the table to see that that status word is here. Status word 6 is a input read. I'm looking at the wrong line, aren't I? MVI, yeah, PC out status. For all of these, it's marking it as 6. Well, maybe it's footnote 6. Yeah, memory read subcycles instruction or data word will be read. So that's not status word 6, it's footnote 6. So we are move immediate R with the data. We get the PC out here, and that's going to be rising sync in T1 with the PC output and the status output. And in T2, status goes away, and we will be hitting the data bus input, and this says B2. Lord knows what B2 is. Some of this stuff is not well defined, but it looks from context like this is byte 2. So we will be receiving data during M2. And it will be written to the data register here during T3. Now, we already have a T-state for take data from temp and put it in a register. In this case, I don't believe that data goes into temp. It would say it here, move immediate M into data. This moves B2 into temp, and this moves temp into data bus. Okay, this is move immediate M data. Okay. So this uses temp, and this goes directly to the register. This is fine. So let's take a look at the memory cycle. The memory cycle should look just like an instruction cycle, except different status and possibly shorter. Where is it? Where is it? Where is it? I don't see it. Halt, reset, hold, operation, read mode, interrupt timing, input instruction, output instruction, basic instruction cycle. Oh, we can use this one as the model. So the input instruction cycle has a byte 2, which comes from the PC. So we are Here in M2T1, we are asserting the address bus, and sync goes high, and then sync goes low in T2, and dbin goes high, and there's byte 2 of the instruction coming in. And now the actual hardware, it just sits there on the data bus until T3 where it gets stored. So looking back at this, how long is it likely to stay there? Well, that's going to be the descending edge of dbin there in T3. Okay, there we've got it. So T1 is PC and sync with status. T2 is increment PC and release sync and bring up dbin. It gives our memory time to respond. And we may have wait states in the middle there, especially if we're executing out of ROM. Now remember, our ROMs are going to pull wait on us. And T3, so we need to set up a generic M2 for fetching byte 2, because we're going to do this a lot. So second byte of, we're going to need an M2 for second byte of address, and that will need to turn over control to the instruction during M2T3. So M2T1 and M2T3 we need to have in the processor so somebody can set those up. M2T1, when we decode the MVI, we're going to have to select the M2T1 for bringing in the second byte of the instruction. And also, we need somebody to set up the 3. And I think during this T1, T2 time is when we can reach out and say, well, we're going to need M2, T3 real soon, so let's use the opcode in IR to select that. So we're going to defer setting M2, T3 until we get into this. Okay, that's how it shakes out. I am going to, at this point, shift this back to the plot and go back to just one page. And we're going to try to make it smaller. Put a zip. And move it off of the screen. I will set it up so the next time I turn it on will appear over on the right here, and we don't need to see the PDF anymore. So this is i8080_mvi.c. And I'm going to start off by creating the MVI file. Mauve becomes MVI. This will not manage the MVI into memory. So this is a, let's see, MVI T4, we just have the one. Okay, and MVI T, this is not T5, it is M2 T3. And we have an M2 T1, MVI M2 T1. We really don't have an MVI T2 T1. What we have is a state underscore B. I'm going to call this B2. So state B2 is going to be our M2, but I can't have it in this file. So I think what I need to do before I start creating the MVI stuff, let's start building up the 8080 internal state that we're going to need to support this. So I did identify a few things. So here we have M1T4, so the opcode table giving the T-state function to use for M1T4. We've got that. That's going to say the X for MVI, which is going to be a different X than the X that we used previously. So this is going to be a x2 function, I guess, which is going to say pick up M2 T1. So opcode, decode table getting the T-stump function to use for M2 T1. And we will set that in picked in M1 T4. Okay. And we are already catching errors during the build. And this, it's not called M1 T4, it's called M2 T1. Okay. So now when we do our build, we say, we're cool again because I fixed the error, which was redefining the same name. So we've got these two tables now. By the way, I fully expect that the cyclomatic complexity of this simulation, just the parts for the 8080, if we did that, I expect that to exceed the complexity of the actual 8080 chip significantly. Because we are not trying to limit the number of functions, we're not trying to limit the number of decision points. What we're trying to do is make it so we pre-decode so much that it's basically direct threaded code. I could probably create a 8080 simulation and ooh, I just got an idea. What if, once we had the 8080 simulating and running FigForth, inside FigForth, we wrote a simulator for the 8080 CPU. I'm not sure it would fit in 64 kilobytes of memory. That might be an interesting long-term project, is to define a microcomputer along these lines using bank-selected memory, which was able to run a simulation of an 8080 CPU. Thoughts? Okay, so there we have it. Now we need to set these up in the initialization code. So wherever I had M1 T4, I want to do something similar for these new guys. M1 T4 becomes M2 T1 and M2 T3. Okay, so we've got the tables. Now that's all that the main 8080 file needs to know about this. I am going to now add a submodule for instructions with the B2. Okay, so here's what we've got so far for implementing the 8080 over here on the right. So I8080 underscore B2. So B2 is going to be provide support for fetching second byte of multi-byte instructions. So multi-byte instructions, I'm not defining as a multi-byte opcode. I'm saying that if you have a 1-byte opcode, which you only have 1-byte opcodes in 8080, if you have that opcode followed by an immediate, like this MVI is going to use, that's a multi-byte instruction for the purposes of this simulator. Okay, so we need void I8080 B2 init. Okay, so now we are starting this off. We've got our tables that we defined here. So we're going to say that if you have a B2, do I need to? Yeah, I need to have I need to export the T state management function for I got a B2, P8080 state underscore B2. Entry T state for M2 T1, M2 T1 handler for second byte of instruction. And that needs to be initialized. C. Did I not initialize those? Oh my goodness. I don't think I initialized these guys. Oh, bad, bad. So I did all of these. I set the state the state pointers up, but I didn't set these guys. Find semicolon, tilde end of line, find white space. The downside of using keyboard macros is that if I'm using incremental search and such, I can blow the macro up so easily by mistake. So C isn't telling us that we didn't initialize fields in this structure. But if we just keep our eyes open, we can mostly catch it. So we now have state B2, which we're going to use for any instruction that has a second byte. So now we see CPU arrow state B2 is equal to and I need to be kind of like fetch in how I do this. This is I8080 state M2 T1. So if I look at the instruction table, I'm not going to flash it up on the screen, but just glance my eyes at it. They're not all the same. This is there's some of them that are going to say fetch from where PC points. There's others that are going to say fetch where HL points. There's others that are going to say fetch from the stack. There's others going to say store something. So this isn't the state M2 T1. This is state B2 T1. And we say static F8080 state. There we go. And this says I8080 CPU int phase. So during M2T1, B2's M2T1, during Phi1 rise, I'm not going to wipe out IR, okay? Phi2 rise, we are going to do the same thing we did here, but this is going to be a different status. Now, this is going to be a status M read because we're reading from memory. It's not an opcode fetch, and it's not a stack read, so it's an M read. And the next state is going to be state B2T2. Let's put some comments in here. B2T1. I'll write better comments later off screen because it takes me a while to actually compose those properly. So address gets PC value, data gets status mread, and we sync. Now the next one is PC Inc, which we are now calling here. This is this comment is wrong. State PC Inc. nsync, start dbin, check ready. So increment the PC, we end the sync, we release the data bus, and we start dbin, and we check ready. And this is going to be state B2T2. And it's going to look very much like this. And if we are ready, we're going to state B2T3. But we're not going to go to state B2T3 because that's in direction, I8080.h. Remember, we're going to grab M2T3 from the CPU. So we're going to index into the next decode table by the contents of IR. We're assuming we can maintain the instruction register throughout the entire instruction. If not, we are going to head over to I8080 state B2TW. Now, PC fetch, state I B2TW. And again, state op read, state fetch wait. So in theory, I could have functions of the same name in different files because they're static. In actuality, if you do this and you're running the debugger, you have two symbols that the debugger needs to know about that have different names, that have the same name in the different locations. So I like keeping my names proper. So I probably shouldn't have called this fetch wait, but yeah, okay. So B2TW comes in and says, if we are ready, we're going to go back to, well, we need to go to the M2T3 state. Boom, just like that. And we are, so re-raise dbn. So in T3, we enter T3 with dbn is still high, okay? And data is ready. So the data is on the data bus when we enter T3. Now, I'm not sure I can test B2 in isolation because if I just add B2 to the system, nobody has registered themselves in M2T3. So literally, we'd hit the M2T3 and we would stall there. We specifically set that up so that any of these T states we haven't defined yet simply lock up the CPU and hold us in that state. And I could test that. I could run some instructions. I could do an instruction that has, oh, there's the other thing is we haven't actually used state B2 anywhere. So we're going to use MVI to test B2. In fact, we have a pending item to test MOV, Once we get MVI done, then we can test move, because we can move immediate into a register. We can move from register to register, and then we can test the value of the resulting register is correct. So what we need to do to support this, we do need to call this function, and I need to have declarations for all of these guys. Boom, 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 just like that. And now if we check our build results, we see that I've eliminated the build errors that were occurring because I hadn't actually set things up. So now we need to call this guy from the appropriate place in i8080.c, which means we need to declare it in i8080 impl.h. Extern void so I am going to sneak this stuff in front. Because I can't test mov init yet, I will keep bumping mov down on the list so that this order becomes an order where the instructions are testable. Okay, so now we are running it. So all this guy did was it said, I am going to construct a state B2 and toss it in there. There's no instructions that use it yet, but it is set up in the CPU structure ready for someone else to pick up. So that the only symbol that this file exports is this init function. That's my attempt to, at least in a small way, maybe reduce the coupling between modules. I want modules to be coherent, but I want to limit the coupling. Now, we are going to be insanely coupled through the internal state of the structure because all of these modules, their job is to operate on that structure. Okay? But I don't want them, you know, if I have an internal state, I don't want somebody else grabbing state B2TW and using it for something without my knowledge. I mean, if I want to share this method across multiple modules, I will either co-locate the code, or I will have to make it non-static, or I will have to export a pointer to it. And it would then become officially a part of the API for this submodule. But until I do that, I'm going to keep it static, so nobody else is supposed to be able to call it. But I think, and yeah, it's quite likely that a lot of this will collapse together. So much of what I'm doing, this, clone to own, where we take a module that's working and we clone it and we make some changes, that's only a useful engineering practice if the stuff you've copied isn't likely to change in the future, or at least if it is likely to change, you are signing up for, I would rather go through the effort of any changes I make, I have to chase down all of the copies and make them, because that's easier than making it generic. And by easier, I mean we need to weigh in the runtime cost of, gee, we could unify these code if only we indirected through there. Well, it's a memory indirection. And our costs are already going up over here. I'm rapidly coming to the conclusion that I want my adder and data types, which I'm using for all the registers and all the buses. I want a way to be able to compile this simulation that excludes those guys running their subscriber lists. Okay, I want to eliminate that overhead because this number, the ROM overhead is now sitting 84 nanoseconds for whatever it is we are benchmarking here. That's beginning to get big. That will require not running those subscriber lists. It may require elimination of the hazard detection and recursion detection stuff on the data bus. If we don't run the lists, then we don't need the recursion detection. we may need the hazard detection. The only way we can eliminate the storage items that support hazard detection is also to eliminate the Z state. So we may, as part of turning that off, we would then lose the ability to have an explicit Z state. But that means that all of the places where we test the Z state in our test code have to be, oh, and maybe we have a function that says I might be Z and a function that says I might not be Z, which can return, I don't know, or the test that tested have to say, well, if we're compiling in fast mode, then we don't test this because we do not have a defined Z state. Okay. So I am going to defer testing of this, and we are going to make a note in the README file. I have a pending items here, assert conditions. We want it to do test the I8080_B2 mechanism. We have some tests here where we're not actually asserting anything, where I actually have to look at the plots and say, oh, that plot looks bad. And that's not something that happens every build. I don't look at those plots every build. That would be crazy, because we're building every time I save the file. I do Control-XS, and boom, it triggered off, and it did the build off screen. And now I can go over, and what we're doing here is we're actually just looking at the logs. We're rerunning the benchmarks, but we're just examining the logs from the most recent build. So we have that to-do item there. Boom. So now we have this B2 thing. Okay. So now we want to implement I8080_MVI.c. And this brings back the buffer. We do not have this state B2. We do have, remember, we started this by copying the MOV into MVI. So MVI T4 is just a state. The table comes in for state_MVI M2 T3. Oh, we have that table here. So we've got state MVI M2 T3 B, C, D, E, H, L, and A. We're not going to do M today. That's more complicated because that's going to be M2 cycle is going to be fetching the byte. And we're going to have to add an M3 cycle, which is store through HL. One thing at a time. Okay, so MVI init. When we call it, it's a destination register that we get handed. And for each destination register, we're going to say M2T3 is MVI M2T3 of SSS. Boom, there we go. That picks up those 8 functions. I am going to write into M1T4 is going to be I8080 state. Oh, we need a we need an M1T4 for that as well. So this is B2 M1T4 and B2 M1 and 2T1. So this is the M1 T4 handler for ops with second byte. 2-byte ops. This is the M2T1 handler for 2-byte ops. It strikes me that we may not need to export this. So this is really just M1. This is really just B2. This is 2B ops. Yeah, 2B ops, 2-byte ops. There we go. Oh, renaming. I8080_2B ops. Is that correct? Ah. Is it possible for me to detect that? No, I don't want to add more code to the X. I don't want to add code to the existing M1T4 guy that says, oh, and to support this inside this piece of really small code, I'm also going to go out and check the, I'm going to go check this table before I say I am the end of a cycle. So we are going to have an M2 bops. Right, and this says state 2 bops. M1 T4 used when we have used for 2-byte opcodes. So during the following thing, we need to set not M1 T1, but state next. It's a T1. Okay, it is a T1, but it's not an M1 T1, it's an M2 T1. Okay. So all this guy does, and this is a T4. Who defined X? Who defined function? Is it in fetch that I got the X? Yeah, there it is. So all this guy was doing was setting the return to M1 internal signal. We don't want to return to M1 because we're not going back to M1. So all we're doing now is we're saying, if we're using 2 bops, then our next state is state B2T1. Okay. And B2T1 says, here we are here, and this is all what we want. The names, however, need to change. Two bops underscore T1, T2, TW. Are we building again? No, we're not, because we're saying state B2. This is state 2B ops. And I have renamed a file, which means I need to make clean to clear out all of the dependency files that are going to give me problems. So now, MVI init, I do need to make this at least compile. And let's look up the correct MVI instruction. MVI is hex 3. No, it's hex 06 with the destination left shifted by 3. So M1T4, which is going to be picked up by 2 bops. M1T4 how did I do this? Yeah, M1T4 of op is equal to CPU on arrow. I do not depend on memory for any of this stuff. And then we go back in here and we say our I don't believe we have an M2T1 anymore. M2T3 is our MVI M2T3 for the destination register. There we go. So M2T1 we don't have a table for. We select the M2T1 strictly in the M1T4 cycle. And if that's confusing to you, I agree, it's confusing to me as well. Now, M1, M2, T3 is M2, T3. So all of these guys that are MVI, T4B, and so on, this is the equivalent of the move instruction with the source, and the source in our case is the instruction set. So all of these things that are picking up the data here. So this is these 7 functions. 3, 4, 5, 6, and 4, L and A. Those guys go away. So this is going to say when we hit one of these operations, then the last T state of the first machine cycle will be this two-bops thing, which says, oh, we want to start a second cycle. And it will do that second cycle. It will get into the two-bop stuff. It will present the PC. It will increment the PC and store it back. It'll present the status. It will then release the status and set up data. So we arrive in these guys with the DB-in signal asserted. And on Phi2 rise, we can now data 2 into our register, but it's not the temp register. These guys are coming from the data bus. And M1 is set, so we automatically will return to a T1 M1 cycle, M1 T1 cycle. MVI BIST, we have a function. We're going to fill this in to test this. I promise. Okay, so MVI T4 does not exist. Now, I-8080 state B2 T2 is MVI state 2 bops. See, my name change, I didn't have my mouse cursor at the top of the file when I changed the names, so I didn't get it elsewhere. And there we go. Nice clean build. And it's running. It's not testing anything. But, oh, the other thing that we forgot to do is I need to make sure B2 has, B2 does not have a test. Okay. Go back to MVI. We have wired these in, we think. Check it over by eye real quick. Move B, C. Remember these 7 functions that I set up here, I wrote a little bit of Python code to generate. I've left that Python code in the bin directory. I actually extracted it from the org file where I was testing it. I just made it a Python file so it can be executed by people that don't spend all of their time in Emacs org mode. C, D, E, H, L, and A. So we now have the ability to put in those 7 instructions. So let's write some testing. So we now have a place to put our stuff. I like to do an op-nop at the front just because we may have a plot immediately before us that was doing interesting things, and I want to give us at least a little bit of margin. We may adjust the dividing line between where we start our plots. But we do need, is it in target? Somewhere we're actually defining all of our instructions. It's an impl. Okay. So we've got all of these mobs. Let's just take this much of it. These are MVI instructions. Whoops. MVI A is 7F. There's a lot of move instructions are just, expensive no ops. Now these guys, oh, never mind. The instruction is 6 plus DD left shifted by 3. Let's go back into bin. I have gen mov. I removed the stuff from here that produced the pound defines, but that's all right. Let's call this, well, let's write a new one. Gen opcodes. This is going to be whole new code. I'm going to just set this up to generate all the opcodes for all the various things we need. So def gen mov. Yeah, I'm going to so we're going to do for each D So the registers as used in the instructions are that. Pardon my being quiet here. X40 plus DDD times 8 plus SSS. I want to recreate the MOV defines before I start creating the MVI defines. Screw it. It's just a Python script. I'm not going to do any fancy functions. So that generates these codes. Let's put an empty string. Yeah. If r sub ddd rrr Okay, so this will not generate the opcodes for M. We'll do that separately. No, we won't. What am I doing? We haven't generated the instruction yet, but that's perfectly valid. And the other part is I want this to be appropriately spaced. So 8 spaces I counted. So there are all of our MOV instructions. That includes MOV RM, MOV MR. Now we want the MVI instructions. That's similar. MVI uses 4D. The opcode is 0x06 plus DDD plus DDD times 8. And if I put an O2 in front of there, it will put the leading zeros on, which we're missing. There we go. And I need a couple more blanks there. And to make this even easier, I'm going to say op string is equal to this. So we are now defining the opcode for MVIM, even though we haven't implemented it yet. That's okay, because we've got our we're just going to bulk define it, rather than having a special, let's define the macros for just these. Let's skip this one, then later on going back and inserting it. Let's just do this. So now I can grab this. Okay, so MVI BIST has an error. It's calling sigplot, actually it's calling clock run until, but it doesn't actually have clock. I haven't commented elsewhere why the headers are included, so I won't start now. But that starts up, and it should have written a figure called BIST MVI if it ran. Image, that's a doc image, and I don't see it because it's not being run. This is in i8080.c that we're going to do this. So we need to do EIDI halt last because it's putting us in a halt state that we currently don't have any way to get from. We're going to do MVI first because that move is going to use MVI. Not yet written will use MVI to help. No, we can just remember that. So we're going to do reset. We're going to use MVIs to set our register statuses. We're going to go into MOV where we're going to swizzle everything around and make sure the right thing goes in the right place. And we're going to use EIDI halt to test things. And i8080 MVI BIST is not defined properly, which means I need to go to i8080 impl.h and put in the declaration. Yeah, there we go. And up here I can see MVI, which has a bunch of stuff in it. And I get a address 2. We get a, let's take a look at what the actual thing is here. i8080 MVI.c. I probably am not running for enough cycles to see the whole thing, but this will give us some data. Oh, give us a moment. So we really did the NOP followed by FFs, and indeed that's what we're seeing here. So MVI AOX1. There we go. Now remember, we do have that thing in the build where we only generate the PNG files if they didn't exist. So I do need to delete them when it's important to regenerate. So what do we see here? 0, and we have a 3E11. Whoop. Okay, so the move immediates. 3E is a move immediate A. That's what we see here. And we get 1, 1. And then we get a 0, 6, which is move immediate into B, 2, 2, and so on. What we are not plotting are our actual, we're not seeing any results on our registers. So 9 times 5 times how many? Well, first of all, each one of these is 9 t-states. So we're going to see 9 times 5 for the NOP plus 9 times 9 times 7 for those guys plus, let's do another 9 times 5 for that guy. Seg fault. We did get some data. We didn't get any data. Probably because this is the first time we've actually executed any of this. Run in the debugger, and I need to run BIST. There we go. So down at the bottom of the input-output here, we see that we did a whole bunch of things at error 2 trying to create log timing because cd ... run BIST. Much better. We see that our output included the dump from the ROM test, which is good. And we got into EIDI halt BIST, and we said run until, run 1, booty boo, booty boo, booty boo, all the way down here to 5.1 rise, which did a seg fault. So this said that we got here into 5.1 rise and CPU was a TS. What? Step run on edge 2 where we were rising an edge on something. Oh, it's at TS. Okay, so it's just the CPU at the beginning of TS. So we are rising the edge of 5.1 and somebody on the list is bogus. So subs are on the 5.1 rise, so the rise is a list. Down. So the first entry on this list is bogus. So this step is 5.1 rise in 8080. CPU. Okay, so this says C1 CPU state print. So we got a P state of 0 here, guys. How do we get that? working our way back up. So we are here inside EIDI halt. I didn't mess with this. Which means that the state got messed with in there somehow. So I'm going to comment that out. Make sure we're still running. Okay. That's good. So it is somewhere at MVI BIST, we're doing something that corrupts that pointer. Or we're not initializing something somewhere, or yada yada. Oh, did we initialize the Two-Byte stuff? I8080.c. No, we never initialized that. So fetch init, and we need to do Two-Byte init. So this guy was never called. Which means I also want to do some assertions in linked. Now, this is important. I want to do an assert pointer non-zero, assert pointer non-null, and assert pointer not equal to. So assert ptr any pointer. And z pointer is not null. And I am going to cast that to a void star there, just to make absolutely sure. So down here, this says pointer equality comparison failed. So there is a weakness in my comparison macros. We are evaluating expected and observed multiple times. So what we need to do is long exp is equal to So there, my assertion macros will no longer evaluate the expressions multiple independent times before testing them. They will evaluate them once at the beginning and do the right thing. If I'm printing them out with long unsigned, no, I don't want to do that. I want to print out long signed like that. Do something similar with the string. Oh, I had a logic error that I didn't catch until I simplified the expression. And this is important to have this string here. If the first character on the line is a hash, does things differently from what we want. This is pointer null check pointer. Observed value is we have some errors here. But we do now have our assert NZ pointer is not null and assert NE pointer, so we can now test. Let's work on this first. 2 bops init is not defined. Undefined reference to 2 bops init. And I had it in there under B2 init. So edge post is now failing. What did I blow up here? Assert op integer. Notice I said if observed, let op expected, and I expanded that to that wrong. So I reversed the order of all of my conditions. OBS op exp. So I could do the same thing with pointers that I did with integers here, because I'm going to be testing equality and non-equality. I'd rather not do it the long way around. Why is this one character too long? It's not, it's multiple characters too long. So if I were to generalize this, I would have to take in the type, like that. No, I would still need to put, I would have too many parameters to put in. I don't want to be multiplying things where it's not necessary. But I do want to set this up for pointer. So we're still getting this abort here. Oh, right, we're getting into something that hasn't been set. That's fine. That's what we wanted to know, and we will trace that when we get to it. So first of all, BIST is going to be doing a bunch of things. Let's turn these back on. init needs to make sure it initializes, actually is linked that initializes the submodules. So we're going to reset and fetch. Let's do two bops. Do fetch first. Fetch, EIDI halt, MOV init, MVI init. MVI MOV EIDI halt. Okay. 8080 impl. Brink, 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 brink. We have this same set of things. We have reset init, fetch init, two bops init. We have MVI init. We have MOV init. We have EIDI halt init. Then we have the BISTs. Reset, MVI, MOV, EIDI halt. Okay. So despite calling those now, we are still hitting something that's not good. Where are we getting this? GDB. So here, state power on, calling from phi 1 rise, oscillator rise, clock 1 BIST, and so on. So downside is I don't know where this is coming from because we're not tracing that stuff good enough. So, what are the chances we have actually written something, logs, timing. Let's clear all of this out so it has to get rewritten the next time we run it. Okay, got that. Going to run BIST. And that says we were doing 8080 BIST. And we have logged no data into our log files at all. Head desk, head desk, head desk, head desk. What are the chances that it's just somebody misinitializing? None. Okay. So it is indeed coming in here. So something I blew up in the initialization. Git diff i8080.c. So we forced reset here in 8080 init. Reset fetch 2 bops state. Okay, that's correct. We initialized M2T3. Then here in linked, called all the init functions for the submodules. Oh, there we go. So these guys initialized up here, not down here. And that's much better. Actually, let's just run this bit of it to make sure we're good. And now let's turn on MVI and MOV. And we're good. Gotta watch out where I reinitialize things, huh? So let's wipe out all the PNGs and regenerate them. It does take a moment. The Python program that generates the PNGs takes a bit to load up. So here is the whole run for the MVI instruction test. Well, as much of it as we traced. So you'll notice that we specified the number of cycles here, and apparently I didn't count enough. But you see that we are coming up with data being written to A, C, B, E, L, and so on. Yeah, that's not executing in the order that I wanted. So 3E, FF, 22, 0E, FF, 44, 1E, 1F. This is stuff going into IR. So 3E is the instruction. We're getting another instruction of FF. What are we fetching here? PC is 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and so on. That's correct. 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D. Yeah. So what I need to do here is run. I'm going to make a bunch of plots independently. T0 plus, I just want to do the NOP cycle, 9 times 5. So here's the execution of just the NOP instruction. So we get PC goes from 2 to 3. Address 2 sees the NOP, NOP into IR, and we get to address 3 here. And what I want to do is roll this back. Since we are starting in the middle, I want to have my plots end right here. Right here, actually. -8, I think. Okay, so that's just the NOP instruction, and that synchronizes us with the closing edge, which is what I wanted to do here. We are going to be changing T0 a bunch of times in this process, so let's move the declaration up. This is move into B, MVI B, actually move into A, and this is going to be 9 times 9. Should be 9 t-states. And to make this easy, I'm going to say RM projects doc image I8080 star PNG. Okay, so what do we see here? We see PC starts out as 3, and there's the address. We get the sync, we get an A2 type cycle, and the instruction is 3E, which gets put into IR. On the next machine cycle, we've got a PC of 4, which goes out on the address bus, and we get data 11, which goes into A. Yay! Let's do B and C as a pair. Okay. Now, what I'm seeing here is we're getting an IR of FF. Followed by a 2-2. So this MVIB showed up as an FF. Interesting. Debian doesn't look normal there. We never got the downtick, so we never got the data, which means we got high impedance data. I'm going to go grab some more coffee. I'll be back in a moment. Okay, so what I'm going to do is, because the first one worked and the second one didn't, I'm going to move the move into A, put MVIA at the bottom. So we're going to start off with the BC register pair so I can take a look at just that instruction. Okay, so we come in here and we see the 06. So our ops should be a 06 and then a 06 with data and then a 0E. So we get the 06, boom. And then address 4, we get a type 82, and we get data 22. So that's correct. We see the 22 going into B. Get address 5 coming out. And is it possible that's not? Oh, look at this. dBin is not falling. Boom. There we go. So, in the M2T3s, I need to drop dBin. So just like I-8080 fetch, the T3 is the op read cycle, and we have to do all of that stuff. But instead of going into IR, we're going into our destination register. So that's why, because we never saw a rising edge of dBin, so the control signal never did squat. Now this is where generating all of these functions with macros would have come in handy, because I could have just edited that into the macro. But I still think that having one macro generate 7 functions, the trickery that we go into in that macro is a little obscure, and I'm going to resist doing it until it's a clear absolute win in terms of maintainability. So we do that, and we drop dBin properly. Now our dBin looks normal, our memory looks normal, the wait states are not normal. Why is wait not being dropped here? Who drops wait state, and why are they not doing it? So 2 bops is raising wait here. Okay, which means if we go into a wait state, somebody has to drop wait. Well, again, I believe this is something that was done in fetch, edge low wait right here. So inside the T3 state, at the beginning of the T3 state, we need to drop edge low. Except these are M2 T3As. Is that correct? That is correct. Come on, Greg. Stop fumbling. What have I missed MVI.png at all? Oh, right. Okay. And we need to go to log trace log timing. So when we remove when we do that removal in our compile command, we need to also remove log timing I-8080 star. There. So that resets all of that stuff. No, because the actual BIST isn't being running here. So if I remove that, I need to also BIST. And that's done over in the other build. So I only need to remove all of the log data when I radically change what I am tracing. When I remove a trace. So there we go. So here's our BC set. We see B is being set and C is being set. 18, so if I multiply that by 3, just call that MVI. How wide does it get if I just do all of them? I can carve this up differently. Why am I getting an FB instruction? I think this size of is giving me a size of a pointer, because we are fetching A2, 06. No, A2 is our sync data, so it's 06, 22, 0E, 00. Yeah, so we're only getting 4, so did I do a macro for that? I did desoc assert. Did stub, I did fail, but I didn't do a show macro. Okay, so size of MVI BIST is 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's correct. So when we did an M copy into cells plus PC value of this program, we should have copied all 16 bytes in. And each one of these cells is a data. How is it? Hold on. ROM 8316.h. Each of them is a byte. Well, the other thing is we are actually not doing anything on any of these, so I'm not sure. Not sure what is going on. Much better. So we now see data being written. 2, 3, 4, 5, 6, 7. So we've got our no op. B, C, D, E, H, L accumulator. So I'm going to break this in half. No, I'm not. I'm going to do this. How much of this do I want to show? If I just chopped it in the middle, okay, so we've got a NOP leading and I want a NOP trailing. I'm going to put a NOP in the middle there. No, I'm not. Okay, we can take this out. Since we now know it wasn't our program that was to fail, it was at fault. Okay, so now I can wrap these up in a single org document. I can bring them into 8080. We want to do A, B, C, D, E, H, L. Fontify, bring them in line, and we see that I'm doing it wrong because I forgot img slash. So let's take a look at what it looks like here. Here is our NOP followed by move immediate into the accumulator, and we see that I forgot to change the order of the program. Okay, so here's the NOP. We can see the instruction register is set to 0. That's correct. And then the next M1, we've got a data. I've got a type of A2, which says instruction fetch 3E. Here's our 3E. And then we've got a memory read, get the 1-1, which goes into the accumulator. Second figure. BC. So we again see a 6 with the type with the data 2-2. And then we see a 0E with 3-3. Now, if this were the actual kinds of logic analyzers that one used back in the late 80s and early 90s for microcomputer design, there would be a facility in it that says, oh, I recognize these instruction cycles for the 8080 because I am an 8080 logic analyzer. And it would actually substitute for these numbers. It would say this is a fetch. It would say this is a MVI into the B register. So it would put the opcodes out. I believe, however, that I am as likely to make an error in the decoder in such a way that if I got an opcode wrong somewhere, I would never see the wrong number here. So we're just going to have to accept the hex values on these plots, cross-check them from time to time, and then double-check that we get the right behavior. So the important behavior for us is our program is saying move 2-2 into B and 3-3 into C, and this is what we're seeing here, 2-2 and 3-3. Now the next one down is D and E, and we do in fact see DD gets 4-4, and E gets 5-5, and the shapes of all this look right, and HL. So I could increase the scale on this, so I could reduce the number of plots while increasing the width of the plots. I think I can actually double it. So A, B, C, we're going to do all in one plot. Plus 9 times 18. ABC, and this is going to be DEHL. And there we go. And this is still, while the scale is getting pretty fine here, we're still readable. We still have room inside this box for the value. I think this is as, well, we're getting to the limit here on how narrow I want to make the plots. And we see 1, 2, 3, 4, 5, 6, 7. So how can I turn that into a built-in self-test that actually tests things? Well, first of all, what I'm going to want to do is run it out to just far enough that the data appears in the register. I'm going to assert that the data has appeared in the register. Okay, revised a little bit. here are my states, my tests for MVI. We've got A, B, C, D, E, H, L. So A gets 1, B gets 2, C gets 3. You see this is happening in the last T state of the instruction. And I'm chopping it. I'm doing 1 clock before the end of the instruction goes on to the next one. And we get 4, 5, 6, 7. And we're now asserting these guys. I can do the same thing as a post now. Difference is, in post, I will not be doing plots. And it is exactly the same thing, except no plots. No trace. BIST becomes post. No trace. And of course, none of these all exist. But I need to build them. So while I am thinking about this, let's do it. Declarations first. T0 set but not used in post. This is fine. So to make these tests valid, I do need to I need to set the registers to something else. The easiest way is to data to CPU A. Yeah, we want to do this because if we set them to the Z state, which doesn't exist in the CPU, the problem comes when we shift to the model that says, don't track the edges. Don't track Z. Ooh, so we're going to set them to FF at the beginning. Okay, so we now have a bunch of things that are not defined, and that's okay, because that's up to us now to build them. So we need reset post, i8080 reset.ac. We have a BIST function, right? We're going to do the same thing, but without plots. What do we want to assert at the end of this? So what does our reset look like? 8080 best reset.png. At the end of reset, I want to assert basically the state at the end of this. So 0 is I'm just going to put all these in resin, reset, reset internal, DIN, ready, PC, adder, sync, ststb, data, dbn, wait, memr, ir. Some of these are not aspects of the CPU. Some of those are inputs. So we are going to assert that at the end of our reset test, reset and ready in got manipulated. Reset and ready got manipulated by the test. Okay. Res in went high. Reset went low. Reset internal went low. So these are things the CPU does, and we're going to move stuff up that the CPU didn't do. Status strobe has nothing to do with, well, it does have something to do with reset, because if we didn't come out of reset properly, status strobe will still be low. But that's something coming in externally. We want to assert that our PC has, by the end of the test, advanced to 2. And we're not going to assert anything about the address bus. We're going to assert that we, at the end of the test, are asserting sync. Yeah. We need to make sure we start asserting sync properly. We are not going to assert anything about the data bus. We are, however, going to assert that dbin has gone low by now, and that wait has gone low, and that memr has been relaxed. We're not going to assert anything about IR. And we need to do these during BIST as well. And I'm going to do those assertions after we finalize our plot so we can get the plotted results of a failed test. Okay. So CPU is undeclared. Oops. I8080 P8080 CPU is equal to TS CPU. CPU doesn't have anything called resin, so we're not going to assert anything about that. CPU doesn't know about ready in, so we're not going to assert anything about that. CPU doesn't know about status strobe, so we're not going to assert anything about that. CPU doesn't know anything about memr. Okay, success we don't use here. Resin, ready in, status strobe, memr go away. And CPU. Okay, so now MOV. That's easy because we haven't written that test yet. So duplicating a non-test is working. And EIDI halt. Again, we take BIST. What do we want to assert at the end of EIDI halt? Well, we are well into the halt state, so assert EQ integer of So again, we don't know about some of these. We could assert the same set of signals here. So reset is unchanged through this entire test, so we're not going to test it. Ready should be 1 at the end. Okay. CPU should be OX14. So if we change our program that we're running here for this test, this value will be different. And I think actually we need to set it based on the initial value here. So word PC0 is equal to, and this is 11, so PC0 plus 3, I guess. We'll find out the first time that runs. So PC is set to there. We should not have a sync at the end of this process, despite us being at the proper point within a ongoing machine cycle that we would have one. Status strobe we don't know about, data we don't care about. Interrupt enable we should have left high. DBN we should have left low. Weight should now be stuck high. We don't know about MR or IR. So that should be enough of a test for us. So now we go up to here and we don't plot. Oh, almost forgot. We need P 8080 CPU equal to TS CPU. In fact, let's just do that. So, plotting goes away. So next thing is EIDI halt BIST is being redefined improperly. Well, that's because I forgot to change the name. How about that? And we have our posts running. And these posts are going to assert the final state. Now, did we assert anything here? We did not assert anything here. We asserted our contents of DE of the registers. I think that is a valid way to test these instructions. Just verify their effect is proper. So does clean remove those trace files for me? do it so it's not behind my picture. So I'm not currently removing the trace files. So log, so log/timing. I want to actually remove all those files and those directions. I don't want to remove the .getIgnore, however. I could use git to remove stuff not under git control under timing. I could make a super clean which would do a git clean -dfx, but that's dangerous because I might have added source files. And I might want to do a super clean before testing. So we're not going to do that. Okay, so clean. Okay, so I want to remove the directories, but only if they are empty. No, let's not. So now I can go into here. I could say make clean. Oops. You make file.rows line 1 missing separator. And that rebuilt and gave us a whole new set of files. Remove PMGs and make cycle. Go back in here and load them up. Okay, so we have our reset plot. We have our MVI plots. Oops. And there, okay. So we have now implemented and tested the MVI instructions. To be perfectly fair, I am going to start building the tests for the MOV instructions. I think that's something that we don't want to have a stream of its own, so I'll just include it here. So MOV. Now MOV is going to use MVI instructions to test MOV. The other thing is we don't need to test all 64 of them. We need to have at least a test reading from each one, at least a test writing to each one. So we're going to start off by grabbing MVI and bringing it in, and I'm going to change the name to Mauve. So initially this would just duplicate the MVI tests. And there. So, reading from each register, writing to somewhere. And we're going to do Mauve AA. Now, moving from register to itself has no effect that we can see. So there we go. So there's our program. Start off by putting everybody to FF. So these guys moves into A and then moves into B. So this is going to be 9 and another 5 is going to be 14 cycles. And I'm going to assert that this goes into B. B, C, D, E, H, L, A. 4, 4, 5, 5, 6, 6, 7, 7. Okay, so that does the asserts. Now something similar, but how I want to show it in plots. These are going to be more cycles. I don't think I want to do 4 per. I'm going to do I'm going to do the first one on its own, then do them in pairs. Like that. First of all, are we still running? explicit declaration of that. Clock.h. Okay, so this test condition is failing. I want to plot this and see what's going on, so yeah, always get the test running with the plots and then derive the other one from it. Okay. Oh, wait a minute. Let's leave the asserts in. I'll just do the plot before the assert. 8080 MVI.c gives us our boilerplate for this stuff. There's our plots, our T0, T0, haha. 8080 code is destination comma source. And I did it correctly when I wrote the macros. I did it correctly. Ah. What do you bet? Nope. Okay. So this test condition is now failing, but we should have this plot printed now. This is called MVI ABC. Nothing plotted. So apparently I goofed there. T0, run until tau plus 9 times 4, run until tau plus 9 times 14. There we go. So if we just let it run without doing any asserts, this is what we get. We get a no op here, and then we get our MVI instruction, which is a 3E, so move immediate to A. And then we get a one, which goes into A. That's good. And then we get the MOV instruction here, 47. And it looks like we did not wait long enough to see the results. That was simple enough. There we go. So, first of all, this is 9 times 5 for the knob. And if I run this in here, this will chop the 0. So we should just see the MVI followed by the mauve. Yep, there's the MVI, which this is the beginning of the sync pulse. And 13, there's our data, 1, 1, which goes into A. And there's our move instruction coming in 47, and our data from A to B there. And here's our NOP followed by it. And now we're going to do them in pairs. So if I did these the other way, so I am moving it the other way around. And I would just move them all up by 1. Down by 1? Down by 1, right. So we're going to move this into B and then move B into A. Move this into C and move it into B and so on. So we can now test these properly. Move the MVI to B, move to A. Move to C, move to A. I'll call this mauve BC. Okay, so I want to change ABC to CDE. And I want to change 1, 2, 3 to 3, 4, 5. Except these don't change. Okay, so move immediate to D, move to C, E, move to D. C and D, 4455. TCU is TAU. Okay, so the first plot is MOV BC, which should show the data coming in. So FF means I haven't set it yet. So we get a 2-2 moving into B, moving into A, a 3-3 moving into C, moving into B. That's good. And we're asserting the final values. Do the same thing with DE. So the first change is D register gets 44, which goes into C, and E register gets a 5-5, which goes into D. And those are being asserted properly. Oops, DEHL, that's correct. So the same thing with HL. So there's H and L being brought in. H gets set, moves it to E. L gets set, and moves it to H. And I'm just kind of glancing at the pattern down here. It looks right. And again, we're testing 7 instructions. So what do we do with the last one? I guess we just do the last one on its own. So clean didn't wipe out all of the extra files for BIST-MOV, did it? No, it did. It did. Okay. So BIST-MOV, I've got A, B, C, D, E, H, L. So here's our MOVs displayed neatly all in an org file. So immediate into B, moves it into A, C into B, and so on. This is the same stuff we just looked at. And there's that one, and that one, and down at the bottom, immediate into A and L, So we have A gets 1, 1, and L gets 1, 1. So we can grab all of this and go up to Mauve Post and drop the plotting stuff. And drop T0, which we no longer need. And I can move all these inserts down at the bottom because our final values, once we have written the value into a register, I don't want that register to have been changed by anybody else. And I think there's going to be an error here on the final move into one of them. And we will see indeed that this failed because that guy moved it in there. So I do need to, in fact, test as we go. I really only need to test that one sometime before the final thing we do, but let's... There we go. There we have it. Now, I don't have any automatic test coverage results. I can't say, oh, yeah, I know I have this big testing package, and it's told me that all of these lines are actually run. I could compile this for gcov and work through that. Is that worth doing? How hard is it to set up gcov? Okay, so let's see if I can do that. So to set up gcov, well, we've got all these commands to gcov itself. When using gcov, compile with the option -- coverage. Oh, we're running at 0. No wonder our benchmark numbers are so bad. I thought those numbers looked low. I think, let's see, for each profile arcs is also a good idea. So now I need to update these guys, so when I do C flags, it needs to include cov. Oh, how about that? It's right here. Apparently I have this old habit of using cov for my test coverage. Not tested, right. Let's make sure all of the object files got rebuilt. There we go. Now it's the BIST run itself that I want to do the coverage on. Why is adder.o in this directory? I must have compiled it at some point. So inside the OBJ directories, we get all these GCDA files and GCNO files. Let's clear them out before the run. Wait a minute. Don't think I can do that. Okay, so GCNO and GCDA files are searched for this option. So graph is NO and data is GCDA. Some of them are built by the build and some are created when you run the file. So let's stop the build loop going. I want to try something. So the target I want to make is just to build it, but not to run it. And I believe I have a way of doing that. Oh, it's not built in yet. How about that? Okay, so there's our compile lines. We've got the coverage and profile arcs going in. So the GCNO files are made when we actually compile it. And now if I do a bin live coding bist, I see that we wrote a whole bunch of GCDA files. So I'm going to remove the GCDA files when I run it, and I'm going to remove the GCNO files before I make the .os, which means I want to do that during clean, where we remove objects. So make clean will remove GCNOs and GCDAs. Bist will remove the GCDAs. And the profile is going to be running gcov. What I want it dependent on is how about log slash gprof dash percent dot log is dependent upon this. Yeah, okay. Okay, so if I just do gprof, well, let's take a look at what this does for the error, okay? So from here, I'm going to say make clean, make profile. A.out no such file or directory, which means there. So I've got the make file up in the upper left. So the image file needs to come next. So gprof $@ less than. And it's not $ less than, it is bin slash $. Don't you hate it when you're modifying the wrong rule? So, looking for gmon.out. So when we linked it, we did include coverage and profile arcs. The other problem is there's a whole bunch of GCC options that talk about profile-based optimization, and I need to make sure that I can skip past all those options to find the ones just for gprof. Except I'm not doing gprof, I'm doing gcov. What am I thinking? Okay, so this says gcov bin live coding GCNO, can't open a notes file, cannot open data file, yada yada bing bang. What do I have in the way of GCNO and GCDA? I've got them in OBJ. Live coding did not drop those. We need to use -lgcov when linking. Call it ccov and lcov. So coverage used to compile link code instrumented for, so it's a synonym of profile args, test coverage, and gcov when linking. It is a synonym for it when linking. Interesting. It's a synonym for fprofile args, so we shouldn't need it. Compile the code. Okay. So supposedly this is all I need to do. Did I forget to put it in the LD flags? No, it's right there. You know, some places I still have the really, really old convention of using braces, parentheses instead of curly braces. Yeah, it's the same thing. gcov create source file.gcov. So really, I was just messing up my gcov command. It isn't bin/star. It is, in fact, objdir star dot what? Source files? What do I pass here? It's in the obj directory. -o is the directory for the objdir might be empty. Otherwise, it ends in a slash, so that's correct. Specify either the directory containing the source files, containing the gcov files, or the object path name. This might be enough. You know what I'm going to have to do? I'm going to have to actually look up on the web an example of this. maybe. How about that? That did something. Creating adder.c.gcov. So it created a whole bunch of .gcov files. Next question is, can I put the gcov files in a subdirectory somewhere? Can I create a directory called cov? So -O says where to put the objects, not the outputs. -T would use standard output. Let's try using gcov -T. So we do all that, and it's going to have this all on standard output with things like source. I think I like to have it in separate files. So we're not going to use -T. However, this does mean what I can write is cov / gcov dash. Oops. What does it create? foo.gcov, right. Cent.gcov depends on obj that.gc. Is it the DAs or the NOs? It's the NOs, right? I think I might be able to just do that. Yeah. So here where we're collecting the objects, which one was which again? GCNOs. So the GCNO gets created when we create the source file. All these rules are going to kind of fail if this stuff isn't set up. So I need to make sure I don't imply that these guys have to exist when they're built. So what I'm going to do is we're going to have this dependency. If you say make coverage, it better work. So to make coverage, we're going to wait until we have gcov. We're going to wait till we have log. Run whatever log. And then we're going to say C $make covs. Covs is going to be covs like that. All this to set up something because I'm not using a framework that does it for me automatically. Like I said, this is so early 90s. And somewhere we need to write the rules for actually doing gcov. Instead of putting it in here, we're going to put it over in here. Cov %gcov depends on obj GCNO, and let's see if that actually does something useful. No rule to make target adder.gcov needed by covs. Okay. So we run BIST. Here. And we wind up with all of these files set up. So we have GCNOs, we don't have GCDAs, because I did something foolish. Who's deleting those? GCC, the GCDAs, run live coding, and there are GCDAs in there now. Make covs. C source percentage. Oh, covder. Right. So gcov-o should be the object directory.
All the worm meat goes to the loop master. That would be me.
Can I get away without that? SNDD. If I sort by date, all the cov files got set up here.
Project done quartermaster.
So if I delete all of them, and I do this again without the make clean, it reruns all the gcovs. And there they are. So now I would want to look in here, and what I want to find are all the places where these 5 hashes in a row exist. So up arrow, a number of that, followed by 1, 2, 3, 4, 5, colon. So now we end up with this. And I want to send that to an awk script that will point me at those lines. So I call it recov.awk.
She's just passing out cookies. What you mean?
Okay, so we have some very specifics here. F greater than 0. Might be easier to do it in Python. Might be easy to do the whole thing in Python, including the grep. So let's see if we can do that.
Okay, I guess everybody else that's not here is close enough. I'm not sure. Okay, I'll let that one in.
Okay, so that gets me the arguments. Okay, so with open of r, comma, r as
I can work on that.
fp. Lines equals fp.readlines. Got to read the whole thing in so I have the line numbers I'm scanning through, even though I probably won't need it. Let's
I think that
take a look at a file over in the upper left-hand side real quick.
that looks pretty good, don't you think? For the array?
Okay, so we do have the line number here.
And Hoolan and
So for this, I'm going to say
or who's thinking?
for line in fp.readlines. Is that really the best way to do this? Python read lines, I think, returns an array. I don't want to do the whole thing at once. What I want to do is read each line individually and process it. So I'm not bringing the whole thing in. So it's
Well, you've got group 1 and 2 should both be getting wind fury, and group 3.
I might be able to just do that. Okay, so that does it for me. Line is equal to strip of line.
Exactly. You fix it, Beaver.
We're only really interested in lines that have 3 hashes on them.
And damn totems is a pain in my ass.
Actually, we're interested in lines that start with a specific pattern. We have stripped off the white space from the beginning of the line, so I use starts with. Now let's not do that. Let's do the right number of blanks here. Okay, so unstripped, but we're just showing the lines that are not executed. So now we want to strip off this leading part. So this is 11 of 11, I think. That's correct. And I'm going to need the source file name. Source is not set. But it's going to be one of these guys, so it's going to be the first line. It's going to be a line that starts with that contains source. I believe that's going to be common across them all. So let's see. It's always going to be the first line, isn't it? Okay, so I want to skip the first one. So sys.argv, so 1:, like that. So the first line has this source equals. 23. Adder.c, there we go. And we know that it is going to be just that. So these are all the lines that are not actually executed. So we're not calling adder bench or clock bench or so on because this wasn't a benchmark run. I wonder if I need to include a benchmark run in my coverage. I think I do. Do I? No, I want to know the coverage of just the BIST, because if benchmark covers something that BIST doesn't, it's not going to be testing it. Which means basically all of this stuff that starts at bench, I can ignore. FIFO. So we're not getting to here. So our BIST is not testing doubling of FIFOs. Interesting. And that happens if prod minus cons is bigger than our prepared stuff. It does get called, but it doesn't get exercised by BIST. So rather than go fix up all the coverage problems now, because they're likely to be large, let's just kind of think about it. So we need to skip over benchmark stuff. See, that's something where benchmarking probably exercised that part of FIFO. So hex, I am not testing the case where hex parse gets that. So these are the sorts of things we're going to catch, is these exceptional conditions. We're going to check, we're going to get this stuff that we didn't get. We're going to get the fact that I'm not seeing lowercase. In fact, I'm seeing hex digit values always getting those top three. We're never getting into this function. Well, we can't get into this function during testing. So mainly this output is most useful if we only look at it on a case-by-case basis as we are setting up to do things. But this does mean that I've got the coverage tool. Now, EIDI halt, we're not getting into state DI at all, which means I'm not actually doing a DI instruction during BIST. That's bad, and I can fix that right now. I'm going to say EIDI EI halt. And this now is going to be 2, 3, 4, 5. Is that correct? So we did add some stuff. 9 times 5 times 7. Let's add more. So apparently this is now failing. Oh, because I didn't fix this. 5 times 7. Okay. So that fixed the EIDI halt stuff. We're not getting here. So this says that when we are bisting, then we are always going from the T2 of 2 bops into T-weight. That's fine. That's fine. That's fine. Well, that's an interesting one. The things we catch when we start looking at coverage. Oh. So that's now covered. And now we see this stuff. Some of this stuff is okay to not test. We'll have to go back and review this when we start looking at coverage. Mostly this should be benches and total failure conditions that are not covered. Yeah, test coverage is rarely 100%, so we won't normally run COV. In fact, I'm going to turn it off at this point. Now, that paragraph right there is a really good reason to move BIST, and to move benchmarking at least out to a separate source directory so that we can control what things we're running coverage on. And it's tempting to move the post and the BIST and the test coverage out. Eventually, I will do that. I think I'm going to do that off camera, because that's going to be just teasing things apart, moving things into a duplicate file somewhere, finding out where I've got internal dependencies that I need to resolve, kind of like how I teased apart the 8080 testing out. So that's going to be kind of a painful thing. And I want to turn Optimizer back on. Thank you. And I'll turn the debugger off so we can now see how fast we're actually moving. So let's turn the looping back on. Do a make clean. Go back to make -c there -k-j cycle. And we're back to running properly. And notice how our numbers are low again. I was worried because ROM was getting up to like 70 or 80 nanoseconds. It's back down to 22. The rest of these numbers are back down to good numbers. So it might be a good idea to print those strings when I'm printing my benchmark. Or P, benchmarking with opt equal %s, dbg equal %s, cov equal %s.
Sorry, I'm still dealing with all this trash loot back here. Give me a couple minutes. That was like, woohoo!
There. So now I'd run a compilation. Oh, iteration 7 invokes undefined behavior. Oh my goodness, look at this. So chip goes from
Pulling
0
Reaver in
to ROM
3,
chips.
2, 1.
Let's take a look what's going on here. Stub
We have a
for
Drake
chip
token for
percent.
Warrior Road Priest Mage. Going to Gloom in 3, 2, 1. Shaman tablet.
So indeed, as we work through
Going to
this,
Cinda.
chip 7 is putting into 63 and 64, which is wrong. So this is +1 and +0.
Then enchant formula for stealth.
The optimizer is an absolute win. I never would have noticed that, and I would have been just writing right off the end of that array.
Going to clock.
So I believe that puts us back to a running state with all of our tests going, our abyss going. We have the potential to turn on coverage if we want it. We've got our optimizer turned back out. I think I am done with implementing MVI and fixing up all of the things that we learned as we were doing MVI and Two-Bops and so on. So I'm going to call that a session, and I think I may call it a day too. I need more coffee. Yep, so I am going to work on adding comments to things, and I will get this pushed up to GitHub when that's done. And we'll talk to you next time. So meanwhile, keep it small, keep it safe, and